We're going to look now at the derivative of a power function. Um, in particular, we're going to see that the regular power rule holds, but let's just go in and let's see if it even makes sense. So again, if we're looking at z to the alpha, and that's really e to the alpha log z. Now this guy again on its own, this is multi-valued, as we saw. So what we do is we take the principal value. So if we look at this guy alpha log z, then this is single valued. And actually, to be differentiable, we want the domain to be the following subset of C. We want to take, since it's defined with the log function, we're going to take the same domain as with log. So we're going to take our branch cut, which is delete the non-positive real axis, so the negative real axis and then 0. And then just for some terminology, the special point here, this is called a branch point. And so what we're going to do is we're going to take all of the green area. The green area is good. I'm just going to get rid of that red portion where we have some issues with continuity if we were to include it. Okay, so that's our domain. So this is sort of all complex numbers except for those that have an argument of pi, and we also exclude 0. Now here, the derivative of z to the alpha, viewed as the principal value, I'm not going to go in and rename functions like in the book, is just, again, alpha times, alpha z to the alpha minus 1. And the way you can go about seeing that is taking the expression, like normal. This is just a chain rule problem. Taking the expression e to the alpha log z, and use the fact that e and log z is analytic here and e is entire. It's analytic everywhere. And so the derivative is, by the chain rule, we differentiate e. Okay, this is differentiating e, but then we multiply by the derivative of the exponent, d dz of alpha log z. And the derivative of log is 1 over z. So this first guy is like a z to the alpha. That's exactly, oh, I don't use red for that. That's exactly our definition of z to the alpha. And then this guy, alpha is a constant, so it comes out, and that's 1 over z. So we have alpha z's, and we have a negative 1 z for a total of alpha minus 1 z's. So, in particular, if we wanted to compute something like the derivative of z to the I at a point, let's say, as in the example in the book, evaluated at 1 plus I, we just compute the derivative like normal, so that's I z to the I minus 1, and then we evaluate it at 1 plus I. All right, so that's easier said than done, right? So this is I times 1 plus I to the I minus 1. Goodness, look at that. Nevertheless, it's okay. We can do this. So this is e to the I minus 1 times the principal value of log of 1 plus I. And so this is I, that's just the definition of exponentiation, right? So that's I times e to the I minus 1 log base e of the modulus of 1 plus I, something we've already seen before, plus I times the principal argument of 1 plus I, again, something we've already seen before. And so that's I times e to the I minus 1 log base e root 2 plus I times pi fourths. And now we have to multiply it all out, which I will do. And let me go ahead even rewrite this I as e to the I pi fourths, or pi halves rather. And then this is e to the I minus 1. Oh, shoot, I got to multiply it out. Let's collect our real parts first. How can we get a real number? Well, negative 1 times log, that's certainly going to be real. And then I times I pi fourths is going to be negative pi fourths. That's certainly real. And then what's all of our cross terms here? We have a negative pi fourths, and we have a positive log e root 2. Okay, you're going to have to go in and check this to make sure I haven't made an error. And then very lastly, we still have this I out front. So we have to add pi halves within the I term. All this is happening within the exponent. So we're going to add pi halves to pi fourths to get to negative pi fourths to get a positive pi fourths. Whew. All right, we did it. We're done. So, we use the power rule to compute the derivative, and then we just had to evaluate a power. And, that's where the hard part is. The power rule's obviously very easy. But nevertheless, we evaluated the power, and to make it a little bit more precise, we also made sure that we multiplied our I in. That way it's just a single exponential guy.